new Washington Ice Age flood science. What have we learned in the last 10, 20 years? Where we're going. So just to set the scene a little bit, this is an image from this Dry Falls poster I'm going to be talking about. We're here near Seattle under the former Puget Lobe. And Dry Falls is, for those who don't know, is in this interesting location right at the edge of the Okanagan Lobe, at the outlet of glacial Lake Columbia, and in the path of the Missoula floods, which went through the channeled Scabland. So this is the scene of the Pacific Northwest at the height of the last ice age, around 16,000 years ago. This is what Dry Falls looked like in 1935, prior to the Columbia Basin Irrigation Project and the creation of a reservoir in Upper Grand Coulee, which is called Banks Lake. And you can see from this aerial photograph that it's just this incredible flood-scoured landscape with no modern river, no source of water that's apparent, and just a stunning landscape that has inspired and stumped people for a long time as to how this was created. Just kind of going through some depictions of Dry Falls. This is an early topographic map, a more abstract depiction of it. You can see contour lines representing the topography of the landscape. And this is something that, what are we?
Oh, just gonna admit people.
Go ahead, people. You want me to do it?
Yeah, anytime that you see anybody.
How do I do that? Participant?
Yep. Okay, we're good.
Okay. And this is a depiction that J. Harlan Bretz, who many of you may know, created. It is a sketch, a block diagram of Dry Falls. And the goal of this depiction was to compare the scale of Dry Falls to Niagara Falls, which he has pictured on the upper left. And Niagara Falls was a system that he understood, or thought he did, as to how it was forming. So he used Niagara Falls as an analog for Dry Falls. He said, okay, this is a river eroded system that forms by headward cataract retreat, where the erosion occurs in that alcove and the cataracts move upstream.
Okay, sorry, somebody was there.
Okay. So I love this depiction. It's very simplistic, but compared to the aerial photograph and the topographic map, he sort of stripped away a lot of the complexity and just highlighted some of the key features and of the landscape. So I think it's a beautiful sketch that helped move towards understanding how this landscape formed. This was Bretz's map of Dry Falls, and it's a top-down view. And here he's color-coded different types of deposits. So the green is glacial deposits. The light yellow tan is flood deposits, and then the reddish brown is this flood-scoured channeled scabland, bare basalt, where all the sediment was stripped away. And then moving into more modern technology, this is a drone-based photograph of Dry Falls by Bruce Bjornstad. And like the aerial photograph, it just captures in a very visceral way So what we did, I was working with my colleague Dan Coe. We used a technology called LiDAR, which it is an acronym that stands for Light Detection and Ranging. It's become a common noun, so you can just lowercase it now. And the way it works, a laser shoots a pulse of light at the ground, and it bounces back up, and the time it takes for the light to be emitted and bounce back is proportional to the distance. So you can use this technology to measure the elevation of the ground and of vegetation on the ground. So left, cartoon of LiDAR. At the right is the resulting data, which is a point cloud of all of these elevations. And this is a really powerful technique in geology. This is a LiDAR-based point cloud depicting the landscape of Beacon Rock. And you can then begin to do things with this data. So this is a top surface model, which would be like sort of putting saran wrap over everything. And you can see how the point cloud has now been simplified into a different 3D model. But what's really cool about this is you can process this data to take away the vegetation and get a bare earth model. It allows you to see through the trees, and particularly in the Puget lowland and in forested areas, this is an incredibly powerful technique for landscape underneath the vegetation. People are failing to mute themselves. Indeed. Minus one. Any questions on LiDAR or?
That first picture
Yeah.
with the snowy things,
Yeah,
the very first one.
the point cloud.
Is that what it actually looks like when the airplane lands and you get to look at the computer?
Yeah, I mean that's the data and it's
that's it.
sort of rawest, purest form. Yeah. Back.
In getting rid of vegetation, does the laser actually hit the ground?
It does. Some of the pulses will so in that point cloud, there's a mix of sort of first returns, but then some of the pulses will find a path through all the vegetation and to the ground.
Same question.
Yeah.
Does LiDAR penetrate the surface?
No. It can penetrate water using a different wavelength of light to depths of tens of meters. There's a different technology called ground penetrating radar that can see into the ground, but that is a ground-based technique where you're dragging a device on the ground directly.
Can it see ice?
Ground penetrating radar can see through ice. LiDAR cannot.
Right.
Yeah.
LiDAR can?
Cannot. Yeah. So LiDAR has been used, for example, to find traces of the Seattle Fault or other faults around here. And here, if you want to look at LiDAR, we now have LiDAR coverage for the entire state of Washington, and it's freely available at lidarportal.dnr.wa.gov. You can download it, or you can just look at it directly in your browser. And there's a lot of discoveries remaining to be made in this data. This is new stuff. And it's also just a lot of fun to look at. So what we did is we used LiDAR to make a new depiction, a new image of Dry Falls. This here is a digital elevation model based on ground-based mapping techniques that were done 50 plus years ago. So if you ever used the USGS topo map, this is that turned into an elevation model. What I'm going to show you next is the improvement you get from LiDAR. So we're looking at this familiar site of Dry Falls by this point. And with LiDAR, you can just see the incredible level of detail. It's like 100 times better. So all of these features that, I'll go back again. It's sort of like putting on glasses for the first time, right? You can see, you're like, wait a second, trees have leaves on them, it's truly incredible. And, you can just imagine that this across the entire state of Washington, there's a lot that needs to be looked at here and much to be discovered. So this is a hillshade model. So it's a computer generated image based on LiDAR where it's showing you what the landscape would look like with the sun at an angle, and you're just seeing the shadows bringing out different features. So Dan and I wanted to create a perspective view of dry falls using this LiDAR. So now we're looking at it from an angle, and we thought this was a nice view that showcases the Twin Cataracts and just this entire complex. And then on top of that, we wanted to show kind of what it actually looks like. So this is a satellite photograph. And so what we're going to do is we're going to combine the elevation data with the photograph to create a visualization. So the first step of that, and this is work I have to give Dan Coe credit for. He stripped out the shadows from the satellite photograph, and then he added that onto the LiDAR. And does anybody notice anything physically implausible about this visualization? Where's the sun?
Oh, it's from the north.
It's from the north. And that's not something that ever happens in the northern hemisphere. So it's just a quirk of perception that having the sun from the north for some reason makes the shadows and the landscape pop out better. I couldn't tell you why that is, but it's true. And then just a little bit more tweaking and adding some atmosphere and effects to make this landscape pop out. And then what we did is we added text describing what's going on, some annotations. And this is a poster that if anybody wants a copy, you can email me and say, I would like you to send me a copy, and I will. It is my job as a state employee to send you one. It's also available on our website. I'll put that up in a second. So this just gives you a sense of how we annotated just brief descriptions of the different features. So for example, streamlined gravel bars, these elongated mounds of gravel were deposited and shaped by the floodwater. So this is perhaps for the education effort, this could be something that maybe is in a classroom and the students could go up and look at and learn about what this looks like and how it all formed. So if you want a copy of the poster, like I said, we typically don't advertise it, but I'm letting you all know that you can say, send me a poster to this address, and we will do it. Or you can download high resolution versions of it at these URLs. And this was kind of our first effort in this direction. We have a bunch of other landforms that have been nominated for making additional posters. If anybody has a suggestion, I'm all ears. As I said, we have LiDAR for the whole state, so there's a lot that could be done with this, and it's a matter of finding time.
When you say LiDAR for the whole state, you're not using the 10-meter DEM anymore anywhere?
I mean, I am if I'm making a very zoomed out map, but if I'm zoomed in and I want that detail,
The high resolution is available everywhere in Washington.
Everywhere, except for Indian reservations where they have it, but they don't want it publicly available because there's cultural. So LiDAR can reveal the locations of cultural resources as well as proprietary information about like timber inventories. So there's some political dimensions to making LiDAR accessible. So you notice on that map, the Colville was cut out and the Yakima was also cut out. So there's a reason for that. Any other questions on the first part of the talk? So, oh yeah, good. In the back.
Okay.
Yeah.
What was the resolution of that image that you got with the LiDAR?
With the LiDAR?
With that had showed all the detail in the rocks.
It's 1.5 foot. Wow. Yeah. And the point cloud has a return density, and then you process it into a DEM. So you could actually make a higher resolution DEM if you wanted to. Yeah. Yeah.
This is not LiDAR based, but is there a depiction of what that land looked like prior to the floods?
That's a good question. So the question is there a depiction of what the land looked like prior to the floods? And there are sort of some. Obviously, the floods removed material, and it's postulated that they eroded down a pre-existing valley of some kind. We don't know. It's been called Cooley Creek. I think Richard Waite came up with that term. And there's tributaries that come into the valley where Grand Coulee is now. So it suggests that there was a drainage valley there, and what exactly it looked like is unclear. So
We're just seeing questions.
yeah, that's what you're supposed to be seeing. But that's something. And then I'm going to touch briefly on the work of Karen Lennig and Isaac Larson, and they've done work to model the erosion of channeled scabland. And to do that, they need to restore some kind of pre-existing topography and then model the erosion of it and try to get to what we have today. Great questions. Any others? So this next part is about just kind of getting a feel for glaciers and glacier water interactions and why these glacial systems produce such large floods, why they produce the largest floods we have on Earth. So to start with, what is a glacier? I'm going to read you the glossary, bore you with the glossary of geology definition. It's a large mass of ice formed at least in part on land by the compaction and recrystallization of snow, moving slowly by creep due to gravitational forces and surviving from year to year. Included are small mountain glaciers, as well as ice sheets of continental size and ice shelves, which float on the ocean but are fed in part by ice on land. And at the right, you're seeing a cartoon depiction of a mountain glacier where there's a surplus of snow that survives from year to year, is compacted into ice, and then begins to flow under the force of gravity and flow downhill. So a glacier is a climate phenomenon that can result where it's really snowy, like it is, say, in the Olympic Mountains, or where it's really cold and maybe there's not that much snow, but it just never melts. So the snow just builds up over time. And then when we scale up to the size of continents, we get ice sheets. And this is a vertically exaggerated depiction of how ice sheets over the northern hemisphere, can you recognize North America and Eurasia, how they built up and decayed over hundreds of thousands of years repeatedly. So I'll let this play a few times just to walk you through what you're seeing. This is a simulation of the last 400,000 years. KYR means 1,000 years. It's a simulation. It's not what actually happened. It's something like this happened, though. And what you're watching is these relatively slow buildups of ice and then rapid deglaciation and another relatively slow buildup. And these are what are called Milankovitch cycles. Every 100,000 years, the ice builds up and then it collapses. And you notice that not every glaciation in this model is the same as the last one. Each one kind of has a slightly different pattern. And the ice sheet that we care about a lot here is the one in Western North America called the Cordilleran ice sheet. This is the Laurentide ice sheet. This is the Greenland ice sheet, which is still here today. And then there are Eurasian ice sheets as well. And, you'll notice that, for example, here in Northern Alaska, there's no ice sheet. Does anybody know why that is? It's really cold up there, right? Too dry, right? So it needs to be wet enough to have the snow, but cold enough that the snow survive. So that's how we get ice all the way down here in Seattle, is that it's wet on the western margin of North America. Yeah, I'm going to show you another simulation. We were talking about this one at the beginning. This is a simulation of the Cordilleran ice sheet. So just to get you oriented, here's the Puget Sound down here, Olympic Mountains, and all these mountains are the Cordillera. So what you're seeing is, this is a simulation that's just for the last 120,000 years. The last one was 400,000 years. And what you'll see is it's two different simulations. The difference is different climate. One is, they're just different postulations of how the climate changed. But in both simulations, what happens is ice builds up over high terrain and eventually advances into the lowlands, like here into the Puget lowland. And you'll notice how even within 100,000 years, this one actually has a lot of buildups and decays. So this is, the more we zoom in, the more complex this pattern of glaciation was. And we were talking earlier how in this model, we think about the Puget Lobe as something that built up from ice over the coast mountains and advanced from the north to the south. And we know that happened from the pattern of drumlins in the lowland, but this model actually has North Cascades glaciers advancing into the northern Puget Sound repeatedly. We don't know if that did or did not happen, but this is what the model is depicting. Go ahead.
You know, if you were outside in the weather during these periods, what were you experiencing? Presumably there were people here during the last glaciation period. What were they experiencing in weather? Was the weather similar, but just so much snow, or was it much, much colder? What was going on?
That's a good question. And somebody's asking about Paul. So how do we even begin to think about a question like that? And one is the geologic deposits, and we have pollen that tells us what plant communities were in existence at different times. So it seems like alpine plants, moved down into the lowland. It was colder, for sure. It may have, but yeah, I don't have a good answer to that, unfortunately. They're, often but the Pacific Ocean was still there, and we know it was somewhat colder, but not way colder.
Still livable cold.
Yeah, and people, I think now the latest thinking is people came down the coast. I think they've moved from that. They've moved away from the ice-free corridor, people coming down the interior of North America. Maybe they were coming down the west coast of North America. But there were people somehow managing to live here during the Ice Age, we think. That's not really my area of expertise, so defer to anyone else. And then, so this simulation highlights a phenomenon in Glacier called surging, where glaciers are flowing ice, and in this depiction, this color ramp shows the speed of the ice flow. So here at the ice divides, the ice is essentially not moving at all. The speed is 2 meters per year. And then you'll see there are these corridors of very rapid ice flow up to 3 kilometers or faster per year. And what you'll see in the model is that these fast flowing corridors, they come and go. So, and they form lobes at the edge of the ice sheet. So this is very dynamic, and there's a lot going on. And
how do they figure that out?
well, we see this in modern ice sheets that glaciers surge.
Right,
And
and how
that
do you know where to draw that little red line? That little red line.
So what's happening in this model, as I understand it, is um, they've tried to create a model that makes surges, and it's a threshold process. So I believe the way it's working is there's water building up, and then it reaches some critical threshold where it allows this corridor to surge, and then that also drains out the water, and the process sort of starts over again.
So they can see the corridor, and that's the basis of where that red line is. That's been dug out. Someone today can see that.
I'm not super familiar with the details of how this model was generated, but it's a computer simulation that was set up to try to create surging corridors
Okay.
to match geologic evidence.
Hold
Didn't look like there was one for the Puget Lobe there.
There's not. No, I mean this model is aimed at simulating the Laurentide ice sheet, and in particular, there are these events in the North Atlantic called Heinrich layers or Heinrich events that are inferred to come from surging ice that dumped a bunch of icebergs out into the North Atlantic. So they're trying to come up with a plausible simulation of what could have caused that to happen. But to me, it's plausible, if not likely, that the Puget Lobe and the Okanagan Lobe were something like this, some corridor of fast flowing ice that developed and sent a lobe, and then it was short lived, and it was sort of a dynamic, not an equilibrium glacier. It was a surge of ice that then quickly retreated. So the point of those slides is to remind you that we often look at these snapshots in time of a static white boundary of ice, but in fact, this was anything but static. It was a very dynamic system that was building up and decaying and surging, and so keep those animations in mind when you look at these maps. None of this was static at all. So, one way we can get a sense of what the ancient ice sheets were like, this is the margin of where the Laurentide and Cordilleran ice sheets reached, is to look at modern ice sheets and see what they do. So this is Western Greenland, and this is what the surface of the Greenland ice sheet looks like on a warm summer day. There are superglacial ponds, superglacial meaning on top of the glacier, and meltwater streams. There's lots of melting going on. And this is a canyon or a deep channel on the surface of an ice sheet. So this is what the Puget Lobe or the Okanagan Lobe would have looked like. And this is in the Arctic. Imagine how much stronger the sun is and 45 degrees north in the mid latitudes. These ice sheets that we had here were melting a lot on the surface. Water is denser than ice, so it wants to flow down to the bottom, and it does so through moulins. These are these vertical tubes. These are holes in the ice, and all of that surface meltwater finds its way down to the base of the ice sheet or to the interior of the ice sheet where it refreezes. Kind of scary to think about. You don't want to go in there.
Adventure kayaking.
Yeah, they have dropped rubber duckies in there, and they come out at the other end. This, I think, is incredible. This is the opposite. This is water fountaining up out of the ice sheet and then draining down the surface and finding it's, look at that. That is a geyser on the surface of the Greenland ice sheet. You guys want to watch that one again? How does that happen? Any ideas?
Weight, pressurized weight.
Pressurized, right? There's water going down somewhere higher on the ice sheet. It's flowing through, and then that pressure head at higher elevation is pushing the water back up and creating
Artesian. Yeah.
yeah. I don't know why it's disappeared.
Wow.
Yeah, look at that. It's a geyser. And we see similar things at the edge of the ice sheet, evidence of pressurized meltwater. Look at that. That water's under a lot of pressure under the ice, and it's fountaining up at the edge. So what did it look like at the edge of the Puget Lobe or the Okanagan lobes? This is a good picture to have in mind.
So is that water coming from surface melt and then getting down underneath? Or is it actually melting underneath?
It could be both.
So the glacier actually traps some heat.
Glaciers insulate the ground, so they're warmer at the bottom typically than at the top. So they're like a blanket, and there's geothermal heat everywhere on Earth that is so for example, in Antarctica, you know, the ice at the top will have a temperature of like -20 or -30, and there's many places at the bottom where it's at the freezing point. So
Are there any
Yeah.
places in like Mount Rainier, the Alpine glaciers, where we see this pressurized water at the?
I'm not sure. Not that I know of. I mean, we see outburst floods from Mount Rainier, I know.
Right.
I don't think we have quite the volume of meltwater that you get in Greenland to produce scenes like this that I've seen. Okay, so now we're in Antarctica, and they're gonna drop a camera down this hole in an ice shelf, which is floating ice at the edge of a glacier. So the glacier is flowing into the ocean, and there's a shelf of ice. We're going down through the ice, and we're gonna go 4 meters of ice with bubbles. We're gonna go into a lens or a pond of water that's trapped between two layers of ice. So there's ice above and there's ice below. You can see the floor there is made of ice, and there's a layer of water in the middle. So there's all kinds of ways that water exists I don't have any videos of subglacial lakes. But this all comes together into a glacial hydrological system where there's melting on the surface. Somebody mentioned geothermal heating. So there's melting at the base. There's lakes under the ice in basins. They may flow into each other. And eventually all this water interacts and can come out at the edge in terms of outburst floods or just regular drainage. So glacial outburst floods, these are something that we see in a lot of glaciers, a sudden, often annual release of meltwater from a glacier or glacier dammed lake, sometimes resulting in a catastrophic flood formed by melting of a drainage channel or buoyant lifting of ice by water or by subglacial volcanic activity. And the Missoula floods were probably the largest known example of glacial outburst floods, but they occur on all manner of scales. And we're going to go to one that happens almost every year now in Alaska, related to the Mendenhall Glacier. So this is the Mendenhall Glacier. It's flowing down this valley. There's a side valley called Suicide Basin that gets blocked by the Mendenhall Glacier. And you'll see that it fills with water. It reaches a critical threshold, and then that water suddenly drains out. And this is Juneau, Alaska, where the flooding from this can cause pretty significant damage and even houses falling into the river from these glacial outburst floods. And this is just kind of a small example of the type of system that Glacial Lake Missoula was. And there were lakes like this along the edge of the Puget Lobe as well, in the valleys of the Cascades. So this is just a normal thing that happens in temperate glaciers. So this is a time lapse over a couple months of that Suicide Basin. I'll play it again. Here's the house falling into the river. Yeah.
Oh my gosh.
Yeah, so this is downstream, and this is all that flood water coming out. You can see trees falling into the river.
Oh,
So this gradual filling, we reach a threshold, and then the ice dam is breached, and all the water floods out in an outburst flood.
oh my gosh.
Yeah. So typical flood volume of this is 0.03 cubic kilometers. The largest Lake Missoula was, does anybody know?
Cubic miles.
Yeah, so 2,000 to 2,500 cubic kilometers. So scale this up several orders of magnitude, and that's Glacial Lake Missoula. And that's the famous one, but there must have been many other glacial lakes related to the Cordilleran ice sheet. If you think about that model where there's all these different Cordilleran ice sheets, there's many configurations and many different outburst floods that occurred related to the Cordilleran ice sheet.
So how often does the Suicide Basin cause this to happen?
I think it's pretty much every year,
So,
but it varies. Yeah.
It's Alaska.
it's Alaska.
Yeah, I believe it has gotten worse in recent years, and it doesn't happen every year. So I just became aware of it in the last few years, and it's kind of morbid fun in the summer. You can watch the webcam of this. I took all these images to make the time lapse, and you can sort of predict, like, okay, I think it's going to happen about August 8th or 12th this year. You can see, okay, it's about where it flooded last year. But it doesn't always flood at the same elevation every year, because the dynamics of how the ice dam fails are not the same every year.
So when the ice dam fails, does it flow over the top of the existing glacier? Or
It flows under the bottom.
under the bottom?
Yeah.
So that's increasing the flow too, through the pressure.
Well, it's a very the hydrograph is such that it rises very steeply. So as the process is that as you open a conduit through ice and water begins flowing, you get frictional heating on the walls of the tunnel, and it enlarges, so that increases the flow rate, which increases the frictional heating. So you get a positive feedback loop where the faster it's flowing, the faster the tunnel is enlarging, and it drains all the water suddenly. So this is part of the reason why these floods are so large, is that behind a tall enough ice dam and in a big enough basin, you can build up a huge volume of water, and then there's this physical process that allows it to drain out extremely rapidly. Another style of outburst flood, so that was a proglacial lake outburst flood. This is a subglacial volcanic eruption outburst flood in Iceland in 1996. I mean, look at this. There's a volcano erupting through an ice cap. And what happened in this situation is, obviously this created a ton of water under the ice sheet, and that water didn't actually flood out immediately. It flowed into a subglacial basin that began to fill with water. And like that Mendenhall Glacier, it reached a critical threshold and all flooded out. So the next image, or the next video, is showing what this looked like at the edge of the ice cap And again, we see this fountaining from pressurized water, an incredible amount of sediment. So this is also a process we have to keep in mind for the Cordilleran ice sheet. In British Columbia, there's an area called the Wells Gray volcanic field that has these flat-topped volcanoes that geometry indicates they erupted under ice. So we know that volcanoes erupted underneath the Cordilleran ice sheet and must have created outburst floods like this. So again, like we're used to seeing these images, but this is a really big suicide basin. It's not shown on this map, but there are lakes in the Cascade valleys that would have flooded out. And then in different configurations of this ice sheet, when it was smaller, there's just innumerable side valleys in this mountainous topography that would have had proglacial lakes that flooded. And then to the north, there's volcanoes in central British Columbia. So this was a hydrologically active ice sheet with outburst floods. Any questions on that part, or just got a few more minutes on sort of where ice age flood science has been, where it is now, and what we've learned recently. I kind of think of it in three eras. There's the famous era of Brett's establishing a catastrophic glacial outburst flood story for the channeled Scabland. He published it in the 1920s, and he fought with the scientific establishment for decades until his theory was accepted by the 1950s. Then in the 60s to 80s, the multiple flood hypothesis came into being. Brett's had a handful of floods. He recognized that there was more than one flood, but I think he thought maybe 4 or 5. And then Richard Waite and Brian Outwater looked into these rhythmic deposits, rhythmites, where they saw evidence for 40 floods in central Washington and up to 90 floods in the Sandpoil Valley in northern Washington. So this kind of fleshed out Brett's theory. And then in the 2000s and recently, numerical modeling. So I've showed you some numerical modeling simulations of ice sheets. You can also model water flow over the landscape. So simulating the actual flood flows. I talked about digital terrain models, LiDAR, isotopic techniques. This is used to date flood deposits, date boulders, and trace flood sediment. And whether we've had the same sort of like quantum leaps forward, I'm not sure is the case, but greater insight into processes, dynamics, and identifying additional flood sources. So isotopic techniques, beryllium-10 dating of late Pleistocene megafloods. This paper, I think this was 2017. So beryllium-10 is an isotope. An isotope is an atom with a specific weight, specific atomic weight, and so a different number of neutrons, same number of protons. And beryllium-10 is an isotope of beryllium that's created when cosmic radiation, so a high energy neutron or proton from outer space, comes in and traveling near the speed of light impacts an atom inside a rock, and it breaks it apart into smaller atoms. And that forms that's the only way that this isotope is formed on Earth. So it tells you, it's kind of like a sunburn for a rock. It can tell you how long a rock has been sitting on the landscape. So that's used to date boulders that were moved by the floods. Glacial isostatic adjustment directed incision of the channeled Scabland. So this was a numerical modeling paper that looked at how the weight of the Cordilleran ice sheet actually tilted the crust of the earth and directed the flow of water into different channeled scabland routes. Upper Grand Coulee, new views of a channeled scabland enigma. This is a recent field guide and study that just puts together a lot of information. This paper, Pleistocene megaflood discharge, this was in 2022. This is numerical modeling of erosion, how the bedrock is removed by floodwater. And this is back to the question of restoring the old landscape and then eroding it away in a model. And then this is my work, Okanagan Lobe tunnel channels, and this idea that in addition to Missoula floods coming from the east, there were subglacial floods under the Okanagan Lobe coming from the north. And that's what we need to explain the flooding evidence in Moses Coulee. So how has any of this changed our understanding of the Ice Age floods? The erosion modeling is suggesting that the floods may not have been quite as large as previous authors thought. Lennick and Larson. So these are floodwater fluxes, or the volume of water per time flowing past a point. Instead of previous estimates of more than 10 million cubic meters per second, they estimate around 3 million. So still a mega flood, but not as deep and not as much water as previously thought. And I'll explain a bit why they came to that conclusion. And then tunnel channels. These are subglacially eroded channels. And the takeaway here is that water from glacial Lake Missoula was not the only source of floodwater to the channeled Scabland. So this idea of smaller flood sizes, some of the first people who tried to estimate flood size, they looked at the landscape, they saw how high the floodwater got, and they just assumed that the floodwater came through the landscape that we see today. So they filled it up to the high water mark. But if you think about how it worked, there was a prior landscape, and the first flood eroded down a bit. And that high water mark was set when the landscape was not as eroded. So high water marks get progressively abandoned as the progressive floods deepen the landscape. Kind of obvious if you think about it. So the flood channels were never actually filled to the brim with water. The first flood occupied a less deep channel. There's a cartoon in a second if you're not getting it. So here's the cartoon. The first landscape is higher than the final landscape. And there's a flood coming down it, and then it deepens the landscape, and progressive floods only fill the landscape to progressively lower elevations. So if you use this kind of model, you come up with lower discharges needed to explain the landscape. Okay, what are these tunnel channels on the Waterville Plateau, and why do they indicate subglacial flooding? Let me show you the map. So this is another digital elevation model, and this one, black is low and white is high. And this is a map of a region of the Waterville Plateau near Moses Coulee. You can see the scale here, 20 kilometers. And what you see here are these channels cutting across the plateau. And if you follow this channel indicated by the red line, the bed of that channel rises and then falls. So for water to have carved a channel like this, water on the surface can't flow uphill. Water under an ice sheet can be pressurized to flow up and over a topographic divide. So it's this pattern of channels that rise to cross topographic divides, and then they interconnect with each other. That's called anastomosing.
Nastamosing.
Anastomosing. Mm-hmm. Okay. So then if you map out all these channels, as I attempted to do, you see this wild pattern of anastomosing channels that cross topographic divides, which are these black lines, and they have a radial pattern that's directed towards the edge of the ice sheet. So this, in Jerome and I's conception, is best explained by water flowing under the Okanagan Lobe. There's thicker ice to the north that's pushing the water out towards the edge, and that's what eroded this pattern of channels. It can't be explained by water flowing over the surface, and it's directed from the north to the south. So Missoula floodwater coming in from the east there's no way for it to explain this pattern of flood eroded channels that are on the Waterfield Plateau. All right, so last thing, almost at an hour. This is just a fun animation that is just another way of visualizing the flood. So this is water flowing over dry falls. You know, maybe it looked like this, maybe not, but it's fun to imagine what it might have looked like. Nick Zentner had some animators create this for him. I believe it took quite a bit of work.
So there's the Kennewick man surfing at the.
I think they do have the RV. Oh yeah, there's that guy. And...
Oh.
Get out.
Don't even blow it.
So I would argue this floodwater is too deep, based on that progressive incision idea, and
Yeah.
there's a building. I think there's one with an RV in it. Maybe. There we go. With the RV.
One.
So that's all I have. Thank you for your attention. Just any questions.
Thank you, Dr. Gombiner.
Thank
So
you.
we're going to do two kind of questions. We'll have questions from the live audience here first, and then following that, we'll take questions in the chat. So if you're on Zoom, if you please put your questions in the chat, we'll get to you in just a moment.
Okay, yeah.
Was there somebody back here?
Yeah, let's start in the back.
Question about LiDAR.
Yeah.
So was LiDAR produced by an airplane flying back and forth more than one?
It typically is, yeah. You can LiDAR can be produced, you can put it's a sensor, it's a laser and a sensor. It could be on anything. It could be, for example, like self-driving vehicles have LiDAR on them, which just spins around and it's ground-based LiDAR. You can put LiDAR on a drone. This LiDAR is collected by airplanes flying back and forth and mowing the lawn.
Can surface-based LiDAR generate the kind of information you showed us about moving rock?
Not quite the same point cloud, but it can. So an interesting thing about air-based LiDAR is that you actually don't image vertical faces because you're going down. So you would need actually ground-based LiDAR to complete the 3D model of this landscape.
Hey, Joel. Joel, can you repeat the questions when they come in, please?
Yeah.
Thank you.
The question, yes, sorry about that. The question was how is LiDAR collected from an airplane mowing the lawn, meaning flying back and forth in a regular pattern? The answer is yes for the LiDAR we use, but additionally, LiDAR can be collected in other ways. So in this image, Dan actually drew in some columns to flesh out that surface. Yeah, follow.
I have more questions, but so did Glacier Lake Columbia drain to the east?
So the question was, did Glacial Lake Columbia drain to the east? If anything, it drained to the west or to the south. It's high, the land is higher to the east. So the lowest outlet for Glacial Lake Columbia was Grand Coulee when it was open. There was a period of time where there was ice in Grand Coulee, which caused Glacial Lake Columbia to, maybe it did drain out at a point further to the east, but to the south into the channeled Scabland.
So where did the water come from for the dry falls?
It came from a variety of places. It came from Glacial Lake Missoula dumping into Glacial Lake Columbia and then overflowing out through Grand Coulee. It came from the Okanagan Lobe itself, draining directly into Grand Coulee.
So different flood.
Yeah. So an important, like a good word for this is palimpsest, which means like multiple things overprinting each other. So anything we look at geologically has a long history of multiple different events happening to get to the place we are today. It's never just one thing created this landscape. Yeah.
Why the dry falls, what we see today, occur right there and not, let's say, 30 miles this way, this way? Is there something about the geology underlying there that made it erode more easily there rather than some other location or locations?
Mm-hmm. Yeah. So the question for those online is why did dry falls occur where it is and not some point 30 miles to the east or to the west? And part of it is that the basalt there is bent in the Coulee monocline, which fractured it and made it more erodible. And that's probably why there was a pre-existing valley there prior to the Ice Age. And so the water was flowing down that valley, which also had this tectonically fractured basalt in it that was more erodible. Yeah. And then it got stuck. I mean, it ended here, but were additional floods to occur, this would continue eroding to the north. So it's sort of a, and earlier that these cataract rims were farther to the south. So it's, yeah.
When you're talking about the older landscape causing the erosion or the first floods would mislead us in thinking there was greater volume. So to carry on with that and the erratics that are at Wallula Gap that are up high, and the people have calculated the volume based on today's topography of what the flood might have been in order to have an erratic that high up on Wallula Gap. Would it also mean that the strand lines in Missoula that indicate the water level in Glacial Lake Missoula, the highest strand line would be related to the earliest flooding, but that would suggest high volume still there because the strand lines are preserved all the way down, and you wouldn't expect. So there must have been successively less volume over time. So the Glacial Lake Missoula was getting less and less volume with time. Otherwise, those strand lines wouldn't be preserved.
Yeah,
I think.
Yeah. Yeah. So for those online, the question is about the high water marks, and in particular the strand lines and shorelines in Missoula, and whether the highest ones are the oldest and the lower ones are younger, indicating progressively smaller lake volumes. And that's the thinking. The level of Lake Missoula was controlled by the thickness of the Purcell Trench lobe, which thinned and diminished over time, resulting in progressively lower lake levels. Yeah.
Another question?
A question? Yes.
In your research, how could you tell the difference between the tunnel channels and like other flooding events that might have happened, were some of the tunnel channels like still underground? Are they like cave systems, or do they just leave like a different pattern on the land?
Yeah. So for those online, the question is how did I distinguish a tunnel channel from any other type of channel? For example, a river carved channel or a surface flood carved channel. So just a tunnel channel is a channel in rock or sediment that's inferred to have formed underneath a glacier from subglacial water flowing. And part of the evidence that those channels are tunnel channels is the pattern of the channel bed rising and then falling, which is difficult to explain from surface flowing water, which tends to just flow downhill. Whereas pressurized subglacial water can be forced uphill and then flow back downhill. Another piece of evidence that that channel network was formed under ice is the overall pattern of the way the channels splay out in what I'm calling a radial pattern. Surficially formed channels tend to form dendritic patterns where tributaries come together into main stems and they tend to follow surface slope. So this channel pattern splays outward and it ignores the surface slopes there. It goes up and then back down.
There would also be no catchment basin either.
Mm-hmm. Yep. And there's landform associations. So that map, in addition to there being tunnel channels, there are eskers, which are these sinuous mounds of sand and gravel that represent tunnels in the ice that were eroded up into the ice, filled with water, and which transported sand and gravel. And so what's left on the landscape is sort of like an inverted river deposit. It's a mound of sand and gravel that filled an ice channel.
What were those mounds called?
Eskers. Yeah, and we have quite a few of those in the Puget lowland as well. Yeah.
So did I understand that Moses Coulee was to some degree eroded by subglacial water flows? And I thought I had understood that it was an original flood channel before the ice sheet had advanced to Grand Coulee. Is Moses Coulee a complicated story, or what's the current view of how it eroded?
Yeah, so the question for those online is the questioner had heard that Moses Coulee was eroded by, I'm just kind of filling in, by Missoula floods that flowed over the surface before the ice advanced to Moses Coulee and diverted the floods into Grand Coulee, or whether it's a subglacial flood story or whether it's complicated. And the answer is that there are competing theories. You could find my paper that says it's subglacial floods, and you can find Richard Waite's paper that says it's Missoula floods that were diverted by the Okanagan Lobe into Moses Coulee. I prefer my interpretation, and I explained in the supplement and in that paper why I don't think the other interpretation matches the evidence we see on the landscape. One issue is that we don't see channels entering Moses Coulee from the path that the hypothesized superficial floods followed. Another is that it's difficult in the hydrologic models to route enough meltwater over the surface into Moses Coulee based on the existing topography. A third is that the flood transported rocks in Moses Coulee don't match the Lake Missoula sources. So in other parts of the channel at Scabland, we see these fragments of belt supergroup rock transported from Montana, whereas in Moses Coulee, we see granitic rocks and high-grade metamorphic rocks that match the geology in the Okanagan. So I'll, I can send you both papers and you can see which one makes the most sense.
Is the relative elevation of Moses Coulee higher than, say, Grand Coulee?
So the question
Have
is,
that floodwater like going up and over divide from Lake Missoula, is that kind of some of the thinking?
mhm. Yeah, so the question is whether the elevation of Moses Coulee is higher than Grand Coulee and if there's a topographic divide between the Lake Missoula floodwater and Moses Coulee. Yeah, and the answer is yes, Moses Coulee is higher, and that's part of the problem of getting Missoula floodwater into Moses Coulee is that there's a high plateau in between, and you can come up with scenarios that make it happen, but they're fairly complicated, and I don't buy them. I'm open to being proven wrong. Yes, in the back again.
So the map that showed us the water flowed under in the tunnel, under the glacier, up Foster Creek, and over the plateau and then down Moses Coulee.
Yeah. I mean, that's what I think happened. I can go back to the map.
On this last question, from Grand Coulee, it then flowed down towards Chief Joseph Dam, but from where Grand Coulee Dam is now, over that high ground and into Moses Coulee.
Can you repeat the question?
So the water flow, based on the question you just had, the water flow from where Grand Coulee Dam is now.
It's here.
Water flow from there over the high ground into Moses Coulee.
So the question is, did water flow from where Grand Coulee Dam is today over high ground and into Moses Coulee? And that is the idea of routing surficial Missoula floods into Moses Coulee, is that so that's what these are. These are the spillover points that were hypothesized by weight, is that water flowed over here and then over here into Moses Coulee. And I would say, if it did, where are the channels aligned with that flow path? You can see that they're kind of going actually perpendicular to that flow path. And then you can see it has to cross these two divides, which you can make that happen. But one thing you need is an absence of Grand Coulee, because it funnels away too much of the water.
Right.
So I would say, yeah, this was a main pathway for subglacial water onto the plateau, but there was also water coming down the Omak Trench and through these channels and coming directly across the Columbia River through these channels on the Omak Plateau onto the Waterville Plateau. So it was coming through multiple routes, and some of that subglacial water, these channels drain into Grand Coulee. So some of the subglacial water was going into Grand Coulee, and then all the channels over here were funneling water into Moses Coulee.
Did Missoula floodwater go through Chief Joseph Dam?
Did Missoula floodwater go through Chief Joseph Dam down the Columbia River? It did. So there was a period of time when the ice was advancing and the ice margin was to the north of the Columbia River, and there were large Missoula floods that came down the Columbia River during the ice advance. And then at a certain point, the ice blocked off that flood pathway. That's when Glacial Lake Columbia formed. And then the Missoula floods started going through the channeled Scabland.
What was that word you had for multiple different things happening?
Palimpsest. 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 Did I get that right? It's a word from like literature,
Yeah.
but I think it applies really well to. I got it from Brian Atwater. He uses it a lot, and it applies to this idea that we're looking at composite landscapes where many events happened, and we see traces of all of them overprinted on each other.
Other questions? Let's see what's in the chat here. Dr. Gombiner, I'll let you see what you see here.
Okay, so Malcolm's question. Yeah, I mean, the idea of the slow buildups and then the rapid glacial terminations absolutely involves the dynamism of the system. I would just say yes. I don't know if there's a follow.
Yeah, I find
Right.
your talk really shed a lot of light, for me, about all the different ways that water and ice kind of play together, and ice sheets have water on the surface, in the middle, and at the base, and I think that our awareness of how much water plays a role in what happens in ice sheets is, seems to me it's fairly new recognition.
Yeah, I agree. In the glacier, is the horizontal movement uniform along a vertical section, or does the base squish out because of the isostatic pressure? Base squish out because of the isostatic pressure. I mean, depends. Some glacier, like cold base glaciers, are frozen to the bed, so there's no horizontal movement at the bottom, and there's more rapid movement higher up. Other glaciers, like the Cordillera ice sheet, are they're melted at the bed, so they actually slide, and in that case, the movement is the same everywhere, but in general, the movement is slower where there's friction against the surface, so at the bed or along the valley walls. I'm not sure about the base squishing out.
Great, and Pat Pringle put in the spelling. I think you had it right.
Yeah.
But anyway.
Yeah.
I got it right.
Yeah.
Let's hear it again. Yeah.
So awesome.
He would do that.
He would. Well, again, thank you, Dr. Gombiner. I really appreciate it.
And I like your theory.
Yeah.
Mary Richards.
Thank you. Yeah.
Hell of a lot of water flowing under the glacier.
Well,